So hello everyone and welcome to this next lecture on Python Power Electronics. And in the previous lecture I described how to install Python Power Electronics in Linux using virtual environment. I'm now going to continue that lecture, and in this lecture I'm going to describe how to simulate a circuit in this Linux virtual environment. So I'm going to start off previously with that, and I'm going to assume that you have either Linux or Windows. This will also work with Windows, not a problem, because even in the Windows lecture I showed how to install a virtual environment. So to start off with, I'm going to describe the same thing here, and that is I'm going to start off with my virtual environment library. Now if you look at the lecture, you'll see that there was a virtual environment directory called Python2 test. So first things first, I'm going to activate my virtual environment. So all I have to do is this source and go into the bin directory of my virtual environment and select activate. So you see here in bracket Python2 test. This means that the virtual environment is active. Now that the virtual environment is active, I now will go into this circuit simulator file. Even in that, in both the Windows and the Linux lectures, I showed how to install this. So just follow the same steps, that is to set up the database. The database is already set up. All I have to do now is launch the server. For that, I go into the simulator and I run python manage.py run server. Remember, if you've not done this before, if you've not started before, you must do make migrations and migrate. I'm not going to do it here because I've already done it. All I have to do is run server, but I would suggest go into the previous lecture and check out the installation steps. So this is it. This means the the server is up and running, no issues. This is the address 127.0.1 and 8000 is the port. So let me go and open a web browser. My preferred web browser is Google Chrome. You can also use Mozilla Firefox or anything else that you prefer. So it is 127, okay, it's already saved, 127.0.0.1:8000. Don't forget the :8000, that's the port. So as before, if I click on simulation library, there's nothing because I just installed it. So I'm going to start off with a simulation. So to begin with, when you start off with a simulation, usually the first step is let's create the simulation files. So I'm going to start off by opening a spreadsheet. Now this is Linux, so I use LibreOffice, which is usually like OpenOffice, the equivalent of Microsoft Excel. If you're using Word, if you're using Windows, just use Microsoft Excel. Or you can even install this in Windows. So the circuit I'm going to choose for this tutorial will be a single phase voltage source, AC voltage source, feeding a diode rectifier, and at the output of a diode rectifier there are going to be two loads. One is a simple resistive load, and the second is a switch resistive load. That means a load with a switch in series. And in this lecture I'm not going to do the switch control. I'm going to only talk about the basic circuit. In the next lecture I'm going to talk about how we can configure the control for that switch. So in this lecture the switch is always off. So to start out with, okay, so the first element will be the voltage source. So let me call it voltage source Vin. Now remember, in this the underscore is the separator. Everything before the underscore is the type of element. In this case it's voltage source. Everything after the underscore is the name of the element. In this case it's Vn. So I would suggest, usually it's always best to name your elements as descriptively as possible, because as your circuit grows it then avoids any clashes of names. So let's call this single phase source 1. Maybe a little too descriptive, it's up to you. It's basically you have to choose how descriptive you want it to be. If you want to just do A, that's also fine. And then we need a resistor. Okay, I'm going to name the resistor the same as the voltage source, this is not a violation. The reason is because the type of element is different. You cannot have two elements of the same type with the same name, because then it's a clash. But you can have two elements of different type with the same name. The reason I'm doing it is because in this case I would like to say that the voltage source has a parasitic resistance. And similar to a parasitic resistance, I would also say that it has a parasitic inductance. So I shall call this inductor. So another thing to note is these names are totally up to you. So I could just name this a little differently. I could take the P out. It doesn't matter. It won't be a violation. This name is up to you. As long as there is no other inductor with the same name, that's okay. So now this is our single phase source. Let's pull this all the way here. Now it's always advisable to leave as much space as possible, to use these wire elements, because if you need at later time to add an element, to squeeze an element in, you can always squeeze an element in between them, whereas if you crunch them together, you don't have that freedom. So now I am going to now build this circuit into 3 different sheets. Now you don't have to, it's not a big circuit, you can put it in one circuit, but I just want to show you how it can be done. So when you're breaking up a circuit into different sheets, you have to connect them together. Now different circuit simulators have different connectors, like in some places there are ports, there are tags, there are all kinds of things. In this circuit simulator there's only one way to connect two parts of a circuit which are not connected together by wire, and that is by using a jump label. So to use a jump label, I have to say jump. The first 4 letters are jump. This identifies the element as a jump. After that, it's up to you. So I could say single phase positive term. Like I said, always be descriptive. Now, since it's an AC source, there's no real positive and negative, but doesn't matter, just for our reference. Now I'm going to name the below one negative, because if I use the same 2, these are shorted, which I don't want to do, of course. Now that this is done, let's save this circuit. So I'm going to save this in my virtual environment. I'm going to create a file, and this file I should name it Diode rectifier. It's totally up to you, it's your folder, but this is your working folder. Everything in this simulation will be in this folder, and usually try to separate your simulations into different folders. And since this is a source, I shall call this source. Now the next part is very important. Here it says what type. If you just say save, it will save it as an open data format. If in Microsoft Excel, it will save it as an XLX file. Remember, you cannot, neither of these can be read by the circuit simulator. It has to be saved as a text CSV file. There are a lot of options. Text CSV. CSV means comma separated value file. And it's going to ask you, are you sure? Because this is not the default format. The default format is open data for document format. So you have to say yes, please do. And then it asks you, what is the field delimiter? Field delimiter means what separates 2 elements. For example, here these 2 elements, what would be separating them? We want a comma, and this is important. Don't change this to any of the other options, it won't work. Keep it a comma. Now the text delimiter means what will wrap each element in the cell. It's a double quote here. It can also be a single quote. I also detect single quotes, but I would say don't bother to change. The rest are okay. The character set Unicode is basically a standard. Once upon a time it used to be ASCII, now it is Unicode. Don't bother to change that. With this, I think we are all okay. Let me click OK, and I have saved the first file. Now that the first file is saved, we go on to the next file. And this file will be the diode rectifier. So the first thing is we need to bring the connector from the previous file. So let's bring that. So I shall copy these 2 and paste them in this file, because I am bringing those connectors from that one to here, from that circuit file, so that circuit sheet to this one. So let me give a couple. Here I need a diode because it's a diode bridge. So this is one leg of a diode bridge. I'm going to copy this and put it here. This is my second leg. So I got to change the name to diode D3, diode D4. As before, you can also name this descriptively, it's up to you, and I would suggest you should name it descriptively. So you can actually make this DREC1 D1. So same thing here, DREC1 D2. To be on the safe side, because what happens is if you later want to expand your circuit, you don't have to go and change the names of all the files, or you don't have to choose weird names just to accommodate these previous names. So the first connector will connect directly to this leg, and that's it. The second connector has to jump over this leg and has to connect to the next leg. Okay, that's how the circuit is. So I need another jump label. So I shall call this DREC1 leg 2. Let's call it, I mean it can be anything, just to know. DREC1 means we are just keeping all the jump labels and all the connectors of this diode rectifier separate. So all I have to do now, copy it here. This is wrong. Wire. So now this is my diode rectifier. To complete this, as before, let me put this in a separate sheet. Okay, so what I am going to do is I am going to put a connector. Let me call this jump DREC1 pos term. That is, this is the positive terminal of diode rectifier 1. And let me just copy this, place it here. Negative term. So it's my positive term, my negative term. This is my diode rectifier. As before, we save it. It's my virtual end diode rectifier, and here I shall call this DREC. DREC is good enough. As before, do not forget to save it as a text CSV file. As before, the same warning, are you sure? Yes, I am. Delimiters, check again, comma, quotes, yes it is. And this is my second file. Now the last file. The last file will be, of course, the load. Now the load, as before, all I have to do first, bring this here. So I have to copy this, bring this here, so that I am now connecting the circuits together. So this is wire. Let's pull this out. So the first and foremost thing, whenever you have a diode rectifier, is you need a DC bus. So that's the first thing I'm going to connect. I'm going to connect a capacitor DC bus. Now, you might think this is enough. All you need is a capacitor. But there's a little problem here. In this circuit simulator, every branch must have a finite resistance. It cannot have a zero resistance. In this case, a capacitor is a pure capacitor. It has no resistance. It has zero resistance. So if I'm going to use this branch as it is, and this is a branch because there's a node here and there's a node here, this branch has zero resistance, and that is a violation. So I have to add a resistor here. This resistor can be negligible. It is just so that the circuit simulator is able to solve it. So I'm going to call this resistor DC bus. Again, this is not a violation because there are two different type of elements with the same name. That's okay. Now that this is done, let's now put a voltmeter. I want to measure this, and I call this V out. So this is V out, and then finally let's now go over here, stretch it further, and let's connect a resistance. Let's call this load 1. And as I said before, there will be two resistances, and this second resistance actually will have a switch in series. So I'm going to call this resistor load 2, and I'm going to put a switch here. Let's call this load 2. This switch right now in this video lecture will not be used. It is simply so that I know, simply so that I can extend it later. So the switch is always off. This resistor is not in the circuit. Now, another thing, since we've done this, we should now put some meters. So I put a voltmeter to measure the output voltage. Let's put an ammeter to measure the load current. So I will call this load 1. And let's save this file. So I'm going to call this load as before. Don't forget to save it as a text.csv file. Same warnings, say yes, okay. Now I forgot something, and I should also put these meters in the source, because right now I'm not measuring anything in the source. So let's put a voltmeter at the output of this source. Let's call this volt source 1, voltmeter source 1. That is, I'm measuring the voltage of the source 1. And let's put an ammeter, because I want to know how much current this is providing. So let's call this ammeter source 1. So let's save it again. So with this, we have now completed our 3 circuits. We have a single phase source. The single phase source, we are measuring the current. It has a voltage source, it has a resistor, it has an inductor. We are measuring the voltage out of the output, and we are connecting it to another circuit. And in this circuit, we are taking that connection and we are feeding it to a diode bridge. The output of the diode bridge is now connected to another circuit, and this circuit is the load circuit. We are connecting a capacitor to form a DC bus, to form a steady DC bus, measuring the output voltage of this DC bus, and we are connecting a load. There is one steady load, one switched load. Switched load is not active now, will not be active in this lecture. So with this, we are now ready to configure this. So let's call this diode rectifier. Okay, I have something, maybe I should do this. It's a diode rectifier with a switched load, which is good enough as a name for this. So I'll just say diode rectifier with constant load and switched load. This can be as descriptive as you want. This is for you, so you can actually put an abstract. If you're actually trying to write like do a fairly complex calculation, you can actually put the abstract of it here. It's up to you. The time duration is 1 second by default. I don't think I need to run it for 1 second. Let's just do 0.5 seconds. It's not a big circuit. Integration time step. Integration time step is the time step at which the circuit simulator solves the circuit. This should be as small as possible. Now, for a normal power electronic circuit, 1 microsecond is good enough. If it's a high frequency circuit like a resonant converter or something which is switching at 50 kilohertz or something, this might actually have to be maybe 10 nanoseconds or maybe even 1 nanosecond, depends. Right? Remember this circuit simulator is a fixed time step solver. So you have to specify the time step. It will not solve it on its own. If it's too big, it won't solve. Now, time storage of data, time step of data storage. This is how often you want to store data. It can be the same as your integration time step, or it can be bigger. The advantage of having a bigger value is your output data file is smaller. Now, it's up to you. Here I choose it 10 microseconds. 10 microseconds is good enough for a circuit like this. Output data file. This is the name of the data file where it will store all the simulation data. I'll leave it as it is. I think it's okay. We can change if you want, you can change it. Do you want to slice the output file? I don't think so, because this is not a big simulation. If it's a big simulation, it's advisable to slice it, because then you can actually plot them separately if you want later. So if it is no, it doesn't matter what the next is, number of slices. The last is extremely important. Now for that, I'm going to tell you how to do it. I need the directory in which these files are. So I'm going to go, it's in my virtual environment, and in virtual environment, this is the folder which I created, diode rectifier. I go into it, choose any file, doesn't matter, and go to properties. And here you'll see there's the name, type, size, and there's something called parent folder. Let's click on this, copy this path, and paste it here. This is the directory. This becomes the working directory of the simulation. The simulator will look for all circuit files in this directory, and it will write any output data files into this directory. So now that we're done, I think we can save it. Let us save it, and if it saves successfully, means it's all okay. If there was a problem with this directory, it would have given an error, but there wasn't a problem, and I'll show you later how those problems do come. For now, let's go ahead. So we are now past the first stage. We have now edited the simulation parameters. Now we have to add circuits. So now we got to add these circuits. So let's first choose them. First circuit, let's create source file. So here we can write single phase source. That's good enough. You don't have to put a very detailed description, just one line is enough. And you have to click on save circuit. It's important because only then it gets added to the database. If you change your mind, you want to get this out, you can click on remove, that's all, and it takes it out, no problem. Add circuit file. Now the next file, and that is diode bridge. So let's open that, and we shall call diode bridge. Again, save this file. Circuit could not be read. Make sure it is in the same directory. So there was some problem. So let me go again. So I think maybe this got removed, or maybe I didn't click on it. So you must make sure this file is here. That means it has been added, and then add this. And so there seems to be a problem. I think I'm choosing the wrong file. Let me go back. Oh yeah. So now here, yeah, it is direct. It was not diode rectifier. I was probably in the wrong directory. Now you see. So that's another thing. If the file is not found in the working folder, it will give this error. That means it will say, I couldn't read the circuit. Make sure it's in the right directory. Now we click, and now it was added, because I probably made a mistake and I added the wrong directory. I choose the wrong file from the wrong directory. We need one more file, and that is load. So I'll just check again. This is the file. Yes, it is. Load. And I shall call it load. That's good enough. And we save it. So we have 3 files. We've added all 3. We are now ready to go. Continue. But to continue, you must do something else. You must process these circuits. You must click on this button. This will process the circuit schematic. What it's going to do is going to check the connectivity. If there was a mistake in the connectivity, if there's a mistake, for example, you spelled one of the circuit elements wrong, like instead of resistor you wrote resistor, that's a spelling mistake, but still it will tell you that this element doesn't exist, things like that. So it's going to check for very basic errors. It's not going to be able to solve the circuit now, but it's important to do this. If you make any change to the structure of a circuit, or if you add an element, remove an element, basically if you change the circuit in any way physically, you must come back and do process circuit schematics. So you see this, it's moving, which means it's busy. It's actually processing the circuit. It comes back, it's done, and here it gives you this message. The circuits do not have any detectable errors. You can continue. Now at this point, I'm not going to go into the details. In a later lecture, I'll tell you about some errors which can come, but that's going to be later, not now. So let's go back to main page. So now that this has been done, now we have to edit the circuit parameters. So let's go here. So let's do it one by one. There's 3 files. It has listed all of them. We go to view components. So view components, first thing, inductor. Inductor, this is the name, this is the position, this is the value. It's 1 millihenry. A little on the large side, but good enough for now. We just want to run the example. We don't care. Ammeter. source 1, this is the name, position A, positive direction towards B. Now let's look at that. This is the ammeter at 1A, the positive direction is towards B, which means if the current is flowing in this way, then this ammeter direction, in ammeter current reading will be positive. That's okay, that's right, that's what we want. So that's okay, we don't have to change it. Now resistor V single phase source 1, position 1F, resistor value 100. Now this is something we need to change. Why? This resistor was a parasitic resistor of the source. This should not be 100 ohms. This is like 10 milliohms. So let's change it. And we will go to, sorry, you can't have a negative number, it will give an error. Let's make this 0.01, that's good enough. Click save parameters, and as you can see, the value has changed. Then comes the voltmeter. Now the voltmeter is a little tricky. You see the voltmeter, the name, position, the positive direction 3J. I'll come to this later, positive direction 3J. Positive direction 3J means that it is measuring a voltage in this direction. So if this voltage is higher, if this potential is higher than this potential, the reading will be positive. That's perfectly okay. That's what we want. All right. So that much is okay. The next part, the voltage level, 120 volts. Now, what I'm going to do is I'm going to simulate a 120 volt circuit. If it's a 120 volt circuit, you don't want the voltage level of the voltmeter to be 120 volts. You want it to be several times higher, just to be honest. It's like a circuit. When you have a circuit, when you're connecting a voltmeter, if the circuit is around 100 to 200 volts, you would connect a voltmeter of 300 to 600 volts. So in the same way here, just connect a higher voltage than 120 volts. It's up to you. You can put 500, 600, it doesn't matter. I know what, I'm going to make it 1000. What difference does it make? So let's save this. The reason is how high the voltage is will decide the resistance of the voltmeter so that it draws the minimal current to disturb the circuit. So this is higher, that's a good thing. Okay. Voltage source, this is very important. Component, this is the name, component position 1D, peak value 120 volts. Now peak value is 120 volts is not exactly correct. We want an RMS of 120 volts. So let's make this 170 volts, because if you do 120 into root 2, it's around 169 volts. Let's do 170 volts. Voltage frequency 60 hertz, North America 60 hertz, the rest of the world is 50. Let's keep it 60. I'm in Canada, so let's do that. Phase angle 0, it's a single phase source, you don't have to change it. If you want, you can put a 120, you can put 90, you can do whatever you want, but doesn't matter. This is a sine wave, by the way, it's a sinusoidal wave. So 0 means it will start at 0. If you want a cosinusoidal wave, you can put 90 or minus 90. That's possible. DC offset, no, it's a pure AC wave. You don't want DC offset. Positive polarity towards 1E. Now let's check this out. This is very important. The positive polarity of this is towards 1E. So it is at 1D, and this is the positive polarity. And that is okay. That's what we want. So let's leave it as it is. So all the remaining value, only one value has changed, that is the peak value, the rest are the same. I think that's okay. Let's save this. So with this we are done. Let's browse through it once. Inductor 1 millihenry, ammeter pointing outwards, that's okay. Resistor 10 milliohms, voltmeter 1000 volts pointing upwards, that's what we want. Voltage source of 170 volt peak, 60 hertz frequency, 0 DC and 0 phase angle, and pointing towards the right, that's okay. We can go back. Now let's do the next one, diode rectifier. So diode rectifier is a little tricky. So you see here, these are the different diode rectifiers. This is diode rectifier D4. It's at position 69. Let's go here. So it is this position. Now in a diode rectifier, the cathode has to point upwards. Okay. If you are not sure about this, go to Google and check out diode bridge rectifier. But in a diode rectifier, the cathode points upwards. And if the cathode points upwards, what this means is direction of cathode 59, and that's correct because it's pointing upwards. The only thing we want to change this voltage level. As before with the voltmeter, if the circuit is 120 volts, you would want a diode with the voltage level much higher. Let's also make this 1000 volts. Okay, so that's done. Diode rectifier D2, also the same, it's just same thing, 16 pointing upwards. This is also okay. If you want, just go verify. If you're not sure, go to the circuit and verify. So 16E is the component position, direction of cathode 15E, which means it's pointing upwards. That's okay. Only thing, I want to adjust the voltage rating to 1000 volt. And these values are totally up to you. You can make it 500 volt, 300 volt, whatever you want, no problem. And this is again 4I, cathode polarity 3I, as before, pointing upwards. And this, remember this is random. So you cannot guarantee that this is the default. It could be 4I and 5I. That's always possible. Anything is possible. So do not take this for granted. Always check. And here the last one, also position 4E pointing upwards. That is cathode polarity towards 3E. So therefore it's pointing upwards. With this, we save it and we are done. So this is the diode rectifier. The last, the load. So in the load, first there is a resistor, load 2. Now let's make the resistor around 10 ohms because we want to draw a significant amount of load resistance current. Save this parameter. The capacitor. The capacitor is at position 8C, positive polarity towards 7C. That means it is pointing upwards. It's not really pointing, it doesn't have a direction, because this is purely for our purpose. And this is a good idea. Yes, if this is an electrolytic capacitor, the positive polarity is on the top. So this is okay. The capacitor value, however, is a problem. The default value is 10 microfarad. I think it should be increased. We should make it 1000 microfarad. So let's do that. 1000.0 e raised to minus 6. That's 1000 microfarad. That's good enough. You can do any value you want, 1100, whatever. No problem. Voltmeter, V out. Position 10E pointing upwards, 9E. Also it's pointing upwards, and that's what we want. Range as before, voltage range, let's increase it. I mean, I'm making 10,000, but make it 1000. It's usually best if you make all the voltage levels to be the same. It's usually the best. It's up to you. Switch. This switch doesn't really matter, but still, let's give it a nice. Now, the first thing is here. The component position 5I, direction of cathode 4I. Now, it's important, let's go back here and let's look at this circuit. This is positive, this terminal is positive, this bus is negative, which means the current is flowing in this direction. A switch will conduct from the positive terminal to the negative terminal. Negative terminal is cathode, and therefore, this cathode direction has to be below the component position. So let's look at what this is. The cathode position is negative polarity towards 4I. The component position is at 5I. You see, that's a problem. If I leave it as it is, this switch will never conduct. Alright? Even if it has a control signal, it will not conduct, because switch cannot conduct current in the reverse direction. So this has to change. So which is what I said, don't take it for granted. These are simply random values. The rated voltage as before with the diode, let's make it 1000. This is when the switch is off. What will be the resistance of the switch? It will be negligible. It will draw 1 microampere for 1000 volts. So for 120 volts or 200 volts, it will draw a much smaller current. That's good enough. Control tag, very important. Control tag is like a unique control name to this switch. And I would say, as with the name of a switch, try to make it as verbose as possible. So I would call this switch load 2. Good enough. Okay. Save parameters, and that we are done. So you see, it has been saved. Ammeter, position load 1, component position 5G, positive current 4G. Now this is a problem again. Why? Because let's come here. This is my load current. As I said, this positive terminal, negative terminal, current flows in this direction. But here it's saying the positive terminal is 4G, component is at 5G, which means it is actually trying to measure a current in this direction. If I leave it as it is, this ammeter reading will always be negative. And well, it's not a problem, we just have to change our reference, but I would say instead of doing that, let's change this to 6G. So now finally, resistor load 1 also, let's make it 10 ohms because we want to draw a significant amount of current. And finally, component resistor type, DC bus. Now this resistance is a parasitic resistance, because remember, the capacitor cannot be the only element in the circuit. So this has to be parasitic, which means I can make it 10 milliamp, 10 milliohm. That's good enough. So with this, I've completed this circuit. You can just browse through it again, no problem. As before, all these, each page has instructions. If you're stuck, read the instructions. So now that we're done with all this, we can now go back to the main page. So now you see it has given several more. There is the option of editing control. Now there is a switch in the circuit, and in a later lecture I'm going to tell you how we can control that switch. In this, that switch is always off. Okay, switch is always off. So, and by default the switch is usually off. Switches, that's how it has been default, because I don't want to keep a switch on for no rhyme or reason. So you don't have to do any control. View output. Now we are ready to do. So the last step, let's go to view output. And in view output, there are several. Like for example, there's a run button. This is to run it. And then there's an add plot button. Now since you are starting the simulation, this is the first time I'm here, you must run the simulation first. So I would say, let's click on the run button and let's wait for it what to happen. Now you see simulation is running. If you want to restart, stop and then click. Now when this happens, I would always suggest go to your command line and have a look. Sometimes there are some error messages, because I'm still working on this simulation. There are some error messages which do not appear on the browser but appear here. Okay, so the simulation will not run. It will give you the impression that it's running, but actually it's not running. So just when this stage, go to the command line and just check if everything is okay, and it appears everything is okay. So now that everything is okay, we can add a plot. So let's do the add plot. So I'm going to call, let's say, first plot, let's look at the currents. Let's call this current plot. That's good enough. So I have to then click start plot to start this, and that's the start plot. So now I now have a plot title. Let's click let's add a waveform to this. So first thing is, yeah, there's an ammeter source. So these are the list of meters which are there. Now in this time I have not added any control circuits. Once you add a control circuit, there is also the option of plotting control variables. That will come later. So now first step, I'm going to choose, okay, it's good enough, I want to see the source current. So let's call this waveform legend. And let's call this ISO, or let's call it IS. Let's keep it simple, short. Scaling factor. This comes if you want to scale this. So if I want to make this variable 10 times its actual size, I can put a variable of 10. This is particularly useful when you're plotting voltage and current together. We are not doing that yet, so this is good enough. So I'm going to save. You must save the waveform. Otherwise, now you see, once you save the waveform, it appears here. Now I can add another waveform. You can add as many waveforms as you want. So what do? We add the load current. And let's call this IL. Again, there is no need to scale them, so that's good enough. Let's save this value. And I think that's good enough. So let's save this plot. And now let's add one more plot where we plot the voltage and the current. So let's do that. So let's call this voltage and current plot. So let's again start the plot, add a waveform. Now here the first one, let's call it VSO, voltmeter source one. Let's call it VS. Okay, and I will save it. Add another waveform. Let me add now the voltmeter V out, because I want to know what is the output voltage. Let's call this V out. Let's also make this one. Something wrong, I clicked somewhere. Okay. So now that this is done, let's save this waveform. And let's add the last waveform, one more waveform. And yeah, let's call this ammeter source. Now here, I'm going to use the same legend, but the voltage is going to be much larger than the current, and if I don't scale it up, the current is going to be pretty much invisible. So I'm going to scale this by a factor of 10. So with the IS, the current is now 10 times larger than its actual value, which means I'm now going to save this, and I'm going to save this plot. So with this, I now have two plots. So to plot, all you have to do is click this plot button. So you see whenever you see this moving here, it means it's processing, so let it process. Now what happens, where is the plot? It doesn't come here, it goes to your working directory. So let's go to our working directory. Let's close this file, and you can see the plot is generated here. It will use the same name as the name of the plot. It will remove all the spaces. Alright, so its current plot is basically, current plot is one word, and all you have to do is click on it, and this is my plot. So you see, this is the source current, which is a spiky current, because that's how the diode input current is, and the load current is this hashed waveform. Okay, because it's a DC, the output is a DC with some amount of ripple, and this is the current, which is almost a DC. So now let's go to the other one. Let's plot this plot. So as before, I'm going to plot, always check here, it's wrong, so let it be. This usually means it has done its work. Let's go back to our directory and let us plot this. So here you see, this is our plot file. So now you see what's happening. Okay, I think I will need to zoom in. So now to zoom in, I'll show you that facility because nothing much is available. So let's zoom in between 0.2 and 0.25. That's good enough. Now to use the zoom facility, come up, specify your start range and your stop range. Okay, and go back and click this same plot. So I'm going to plot this again. So it's going to use this range, and it's created a plot, and this is the plot. So there is, apparently there is some amount of problem. The reason is we probably have a very large, I think what is the problem is we have a very large inductor, and that's the reason why there are all these spikes, and every time the diode starts conducting, the voltage just dips. That's probably the reason why. But you see, this is how it is. The source current is spiky. The output DC current is, output voltage is a DC with a large amount of ripple. And the large amount of ripple is mainly because of the large inductor at the AC source. Because when you have a large inductor, there is a huge drop across that inductor. And similarly, the source voltage, the source voltage drops so much because there is such a large drop across that inductor. So all we have to do is change the inductor and we are good to go. But this shows that the circuit is working, the simulation is working. And I think that's it for now. So this simulation, now I don't know how to do this, but this simulation will not stop on its own. So you have to, it will keep, the stop button will never actually become disabled or something. You must click on stop. So if you want to now you can always rerun the simulation, but that's not necessary. And I think with this, I more or less described this circuit simulator. This is all for now, and I hope this lecture is enough for you to get started with using the circuit simulator and how to actually navigate the different pages. What are the values you need to add? As I said before, every page has instructions. If you are stuck, read the instructions, not a problem. So with this, I'm going to stop for now. The next lecture will be on control, and maybe there'll be one more lecture on bug fixing. I'll show you what are the usual bugs which are there and how you would fix it. Or maybe the next lecture will be on bug fixing. The third lecture will be on control. I'll figure that out. So thank you so much for viewing and see you soon. Bye bye for now.